Alright, this is Mr. Anderson for Math 130 Statistics, the first of two videos to cover Chapter 5. In this first video, we'll be looking at sections 5.1 and 5.2. In 5.1 is a pretty short section talking about probability distributions. And to read this to you from your worksheet that you have, either downloaded from the Moodle site or you got it in class, we have found mean and standard deviation of small data sets. But what about sets with infinite size? Is it possible to predict the most likely value of an event? Now, what's great about this is that we can figure out things that have to do with lottery or casino odds, population, or insurance. Because instead of just looking at a small group, we're going to look at a group with an infinite size. Now, we're going to review some information from Chapter 1 here. The discrete variables are those that are counted, and continuous variables are those that are measured. So let's take a look at discrete variables that are counted and continuous variables that are measured. A discrete variable is something that can be counted, like the number of people who buy something. So for example, you can count how many bought a certain amount of food that day, or a certain item. Numbers of sales can easily be counted. So the top 10 albums is by sales, or games, or cars, for example. Now, the next example here is going to be, continuous variables are things that are measured. So, for example, they change. For example, your weight, for example, is something that needs to be measured, and it's a continuous measurement because your weight's not going to stay the same all the time. Same thing with temperature, or you can know at a certain moment what the temperature is, but it's something that needs to be continuously measured, and that's the difference again between discrete, which things can be counted, and continuous variables, those that can be measured. Alright, let's take a look at some discrete probability distributions. Now, this is straight from the book, and I'll read this slowly. You can feel free to pause the video to copy this down. Discrete probability distributions contain the values of a random variable and can assume the corresponding probabilities of the values. I'll say it one more time. Discrete probability distribution, they contain the values of a random variable and can assume the corresponding probabilities of the values. And when we talk about probability distribution, the probability distribution is between 0 and 1. All probability distribution has to be between 0 and 1. And when you add up all the probabilities together, that makes a total of 100%. So to have a discrete probability distribution, you have to have all the probabilities that add up to 100%, and none of the probabilities can be anywhere above 100% or below 0%. So mostly in this section, you're going to see homework that deals with something like this. Let me zoom this out a little bit. Hold on a second here. Oh, looks like I am stuck here. Sorry about that. I guess I have to move this and talk to you about it. Suppose a box contains bills of different values. There are 10 of the $1 bills, 5 of the $5 bills, 3 of the $10 bills, and 2 of the $20 bills. Make a probability distribution chart for the data and draw the distribution. Well, the first thing I would do is make a table. The table having on the top of it all the different types of outcomes from pulling a random bill from the bag, and then the bottom would be the probability of that happening. Now, from the story problem, I found out there were 10 $1 bills, 5 $5 bills, 3 $10 bills, and 2 $20 bills. That obviously makes a total of 20 total bills, 10 plus 5 plus 3 plus 2. And so now I have the probabilities in non-simplified fractions, and I'm going to make my probability chart. The probability chart, you kind of have free reign as to how you're going to label your y-axis. Since I chose, my highest was 10/20ths, or 50%, I chose to go by 10 increments of 20s, and you could make these into simplified fractions, you can make these into percents, but the x-axis is going to be your outcomes. And your outcomes are going to be those all the values, and you'll notice that all those values, if I take the 10 out of 20, the 5 out of 20, the 3 out of 20, and the 2 out of 20, it's going to add up to 100%. So really in section 5.1, they're going to be quizzing you a lot on what is a discrete, what is a continuous variable, to determine if some data does qualify for it being in a probability distribution, and a lot of homework problems that are going to basically ask you to do a picture like this. Notice this is not a histogram. This is actually a line for each type of outcome, and the probability is on the y-axis. Now let's move into section 5.2. And I will start off with a clean sheet here. In section 5.2, we're going to talk about the idea of getting an average, or the mean, the variance, and the standard deviation, and also we're going to talk about something called expectation, or the expected value. Now, here's the thing. Instead of looking at a small population, we're going to be looking at the entire population. So we're looking at infinite size possibilities. Now, instead of using the x bar, they're going to be using the Greek symbol mu. So when you see the symbol mu, please understand that that is the term for the average, but the average is out of a set that's infinitely big, or the entire population. So this is copied right from the book, and I'll read this to you. Hence, to find the average or mean for a probability distribution, you must multiply each possible outcome by its corresponding probability, and then find the sum of the products. Round to one more decimal than you see in the problem. So this is our normal bound rules. So let me show you how that's built here. You must multiply each outcome. So you're going to take your outcome x, multiply it by your probability, which is given by p of x, and then add all of them together to find your average. And I will use the sigma to show that I'm adding up all of these multiplied products. So I'm going to take my outcome, multiply by its probability, and add all those up. This is also going to give us our expected value, and we're going to talk about that near the end of this video. So let's start off with something pretty straightforward. Rolling a six-sided die, what is the average roll? Now, you may not have thought of this here, because when you think of rolling a six-sided die, you just think that, well, there are 6 sides on a six-sided die. 1, 2, 3, 4, 5, 6. And then you think to yourself, well, each chance has a 1 in 6 chance of happening. So that's 1/6 of happening. This is not a loaded die, so each of these are equally likely, 1/6, 1/6, 1/6 for all of these here. And finally, 1/6 there. Okay, so we have a 6th for each of these. So let's take a look at how are we going to find the average roll. Now, you may not think to yourself of like, oh, there's an average roll for these dice? Yeah, there's definitely an average roll. If you do this over an infinite period of time, then the average roll is going to be a number. And let's show the work to get there. Now, the first thing we're going to do is we're going to take the outcome, which is 1. See, we're looking at our formula here. It's our outcome times the probability of getting that outcome, and we're going to multiply that by 1/6. Plus, our outcome is 2, and that's going to be multiplied by 1/6. So you can see that it's taking the outcome, multiplied by its probability, and then add all these together. Here we go. 3 times 1/6, plus 4 times 1/6, plus 5 times 1/6. Sorry, put a line there. Plus 6 times 1/6. Now, if I multiply all these together and add them up, then I will get that average roll. Now, just because I'm going to do this quickly, just to explain, if you don't have a graphing calculator or a powerful calculator, these are pretty easy to do, because multiplying fractions, not a problem. Top times top, bottom times bottom. So this is 1/6, this is 2/6, 3/6, 4/6, 5/6, and 6/6. So if you add up all those together, you get a total of 21/6. And then if you divide those numbers, 21 divided by 6, that is going to give you an answer of 3.5. And that right there is our average roll of one die. That is, the average roll of one die is 3.5. And you might think to yourself, 3.5? Well, I only have a 3 and a 4 on a die. But the average roll of rolling a die infinite times would be 3.5. And if you're still wondering, like, how can this be true, think about when they talk about, like, populations of American families, and they say the American family is now 2.5 kids per family. Well, you can't have a half a child, but it just means that when you hear a number like that, like the average number of kids per family is 2.5, understand that there are most families with 2 and 3 children, and that would be right in the middle. So let's take a look at something that isn't so, well, I don't know, dice-like. So we're going to take a look at the average number of trips that Americans take that are 5 nights or more per year. And we'll see that 6% actually take no trips that are 5 nights or more. 70% take 1 trip that's 5 nights or more. 20% takes 2 trips 5 nights or more. 3% takes 3 trips 5 nights or more. And then 1% takes 4 trips or more for 5 nights or more. So we have our percentages. All of these add up to 100%. 6, 70, 20, 3, and 1. All going to make up that 100% right there. And now what we're going to do is show the work for that. So our outcome is 0 times our probability, which is 6%. So 1 times, and I wrote that a little low there, 0.06, plus 1 times the probability of 0.70, plus 2 times the probability of 0.20, plus 3 times the probability of 3%, or 3/100ths, plus 4 times the probability of 0.01. All right, now that right there, if we multiply all those together, we get an answer of 1 and 23/100ths of a trip, and that right there is going to be our average. So if we take a look at it, that infinite size set, we can say that Americans will take 1.23 trips a year, which means that there are people who will take more, but it's closer to 1 trip per year. But there's enough people who take 2, 3, and 4 to skew that average just a little bit higher than 1. And now, we've done our averages of a die roll, and we've done our average of the number of trips per year. But we don't know how spread out these are. So what we're going to do is find the standard deviation of these groups, and it will be useful to show how spread out these numbers will be. Now, the last time I taught about a standard deviation, I made you make this giant table, but unfortunately that's going to be quite difficult to do. So I'm going to have you use a shortcut. Now, I'm going to do this. I'm going to put a little square by it and give you the variance formula. The variance formula is going to look a lot like what we did before. Except instead of going our outcome times the probability, we're going to go the outcome squared times the probability. And then when we get done with that, we're going to subtract the average that we found squared. So this new formula to find the variance is going to be to do the same process as we did before, except square these and then subtract the squared average. Now that's to find the variance. To find the standard deviation, we would just take the square root of this whole operation. So the square root of the sum of the outcome squared times the probability of each outcome minus the average squared. And that's all under the square root. So please take the square root very, very last. We work from inside out with parentheses. So what we're going to do is find the standard deviation of the dice rolls and the trips we took. So the process starts out like it did when we were finding the average, except that instead of going 1, 2, 3, 4, we're going to go 1 squared times 1/6, plus 2 squared times 1/6, plus 3 squared times 1/6, plus 4 squared times 1/6, plus 5 squared times 1/6, plus 6 squared times 1/6. Then we're going to subtract the average that we had found in the previous problem. In this problem it's going to be mu again. And so that mu is, I shouldn't have wrote mu, I should have just plugged in what we found for that problem, which is 3.5, and we're going to square that. Now I've done all the calculations out, so I had them ready to go, and this variation is going to add up or add up and multiply to 2.92. So the variation or the variance in that die is almost 3 from that average. But let's do the standard deviation. So we take the square root of the variance, and then we get our standard deviation of 1.71 is our standard deviation. So our die is basically one standard deviation above and below the average of 3.5 is almost 2. So you're still going to expect to see die rolls average out to about 3.5 within a variation of 1.71 above and below the die roll. Now let's look at the trips. This is going to be a little bit more interesting since we're not dealing with the die roll here. We're going to take, instead of going 0 times 0.06 or 0 times 6%, 1 times 70%, we're going to go 0 squared times 6%. And I know that's 0, but I'm just going through the motions, folks. 1 squared times 70% plus 2 squared times 20% plus 3 squared times 3% plus 4 squared times 1%. And just don't want this to kind of get crossed off there. We're going to subtract our average squared, which was 1 23/100ths, squaring that. All right, now here we go. Going to find the variation there. The variation is going to be, if you compute all of these in, and I've done this for you, that is going to be 417 thousandths. And if you take the square root of this to find our standard deviation, this is going to be 646 thousandths. Or if you take a look at what this means in our problem, people take a trip about 1.23 trips a year with a standard deviation of about 0.64 above and below. So on the high side, close to 2 trips, and on the low side, less than 1 trip. So the group isn't very spread out according to this standard deviation here. So everybody's pretty tight together. All right, the last part of section 5.2 is going to deal with the expected value. Now, the expected value is the theoretical average of the variable. And this can be very useful. So we're really finding mu, but we're going to have some pretty cool tricks with this here. Like one thing we're going to do is find something called fair price. And fair price is kind of fun with expected value. So let's make a dice game, and the dice game is going to give you $10 on the roll of doubles. So you're going to win, this is your outcome, $10, and your probability of winning that $10 is going to be if you can get the odds of rolling doubles, which is 1/6. Now the reason why it's 1/6 is because on 2 sets of dice you have 36 outcomes. And there are 6 doubles. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So 6 out of 36 reduces down to 1/6. Then your loss is going to be 5/6 then, but you're not going to make any money from that, so that's going to be 0 times that. Now, what we'll do is we'll add these together. So 10/6 plus 0/6 is going to be 10/6. So my answer is 1.6 repeating. But this is my expected value. That means the fair price for the ticket is $1.67. So if I charge $1.67 for this game, this is a fair price, because that will essentially mean that if I play this game an unlimited number of times, an infinite number of times, I won't make any money, nor will the place that's doing this game will make any money either. Obviously, there is a little bit of debate, because since I rounded that from $1.66 to $1.67, the gaming place is going to come out a penny ahead in the long run for an infinite number of trials. So that right there is the fair price. Now, what we'll do is take a look at this process, but instead we'll change the question a little bit. Here's a lottery. A lottery sells 5,000 tickets at $10 each, offers one 10,000 prize, 1 $1,000 prize, and 10 $100 prizes. Find the expectation when someone buys one ticket. Now, what we're not doing is looking for the fair price. We're looking to see what the expectation is after buying a ticket. So we're going to pretty much go down this idea of finding the average, but we'll take a little bit of a twist at the last step to figure out what is the expected value of that ticket. So what we're going to do is start off with the $10,000 prize, and that's going to be, the odds of winning that is 1 out of 5,000. So you see where this is, just like finding the mean here. Then we're going to add to that the one prize that's for the $1,000 prize, which is 1 out of 5,000 again. And then we're going to add in for the $100 prizes. There were 10 of these, so I'm not going to reduce my fractions here because I want you to see where this is coming from. This is coming from, there's one $10,000 prize, one $1,000 prize, and 10 $100 prizes. Now, if we computed that, we could find out the fair price for this game. But again, we're not looking for that. We're actually asking, find the expectation when someone buys one ticket. So we're going to basically take our answer here and subtract the price for one ticket to figure out what the expected value is. And if we compute that in, you can pause the video and try it yourself, your answer is negative $7.60, which means that you will be spending about $7.60 every time you buy a $10 ticket. If you bought all the tickets, that's essentially what your cost per ticket really is, because you win the prizes. However, you're losing that much per ticket, since you're going to the people who are making this game are going to make more money. Anybody who creates one of these raffles here is going to pull in more money. Think about that, $5,000 times 10 bucks. Then what they're giving away. If you don't actually do that, you're going to lose money. So all games of chance in the casinos are going to have a negative expected value, because if that was positive, then Vegas would lose money. So any fair game will have an expected value of exactly 0. So in the previous example, if I actually charged a fair price for this game, and I charged $1.67, then my expected value would be 0, because I wouldn't be gaining or losing any money over this game over the long period of time. So when you are asked in your homework to talk about the expectation when someone buys a ticket, you take your average and subtract the price of that ticket, and that will tell you the expected value. And you can look in the book too. Near the end of section 5.2, there's a fantastic paragraph that talks about the expected values of playing games in a casino. And I suggest that reading for all of you who expect to hit it rich in Vegas instead of realizing that the numbers are kind of stacked against you. All right, that ends video number 1 of 2, and we're going to pick up the second video talking about section 5.3, the binomial distribution.